Okay, let's get started. So yeah, today will be midterm review. Oh, and something else first. So there are people who. So sorry about the announcement being a little ambiguous. So there are people who think that you are not required to turn in homework 5. Actually, homework 6 is the one you don't need to turn in. So, but I think in our policy we say that everyone can get rid of one of the lowest score. So I think if you forgot to turn in homework 5, then you can use get rid of the lowest score one, and you just need to remember don't miss our homeworks, and you should be fine. Okay. Okay. And so any question before we start the review? The review will basically go over all the important formulas for the first 3 chapters. Okay? If not, then yeah, let's go through this. So start with the definition of energy and power for a signal. So this is a chapter over the energy and the power for electronic signals. So we are thinking, say, if your signal is your voltage or current, the energy is going to be proportional to the absolute value square of your the power is going to be proportional to absolute value square of your current or voltage, and we are omitting the constant, so we think the power is the absolute value square. So energy is just this integral or summation of power at each time. So energy over some period is this integral of signal absolute value square or summation signal absolute value square. And then average power is just the energy divided by the time interval. So this is pretty clear. And then there are these things that we have done more calculation on. So there are 3 operations we can do to our signal, and we do them a lot. So the time shift, time reversal, and the time scaling. So this is when you so time shift is where you shift your signal left and right. So you either delay or advance your signal. And here we have very intuitive pictures. So if you go your signal x of n, you change it to x of n minus n naught. And if n naught is bigger than 0, then your signal will shift to the right. Shift to the right by some amount n naught. So you can see here. So this is a delay signal. And otherwise, if you are getting a signal like t plus t naught, and then your signal will shift to the left, and so this is an advanced signal because your signal are happening faster in time. Okay, and then time reversal means that you change from your signal of x of n to x of minus n, and what this do is your signal will flip left and right around this 0 axis. Okay, and similarly, so for continuous time x of t to x of minus t, you flip and left and right around your t equal to 0 axis. And there is time scaling. So you go from x of t to some x of some at, and think that if your a is bigger than 1, then your signal gets squeezed. So your signal starts with this, squeeze into this. And if your t is less than 1, then your signal will stretch out. And if your signal is negative, so then you are combining time reversal and time scaling. And but this one is more tricky. So for continuous time, it's just this squeezing and stretching. But for discrete time, sometimes the time scaling is undefined because unless your scaling factor is an integer, because say sometimes if you stretch your signal, then sometimes you need to calculate x over n minus n over 2, but x of 1 over 2 is not defined. So because discrete time will only take points at integer values, then so time scaling is not always defined. Okay. And then we have this fun problem that you probably do a lot of exercise. You have done a lot during homework where you combine the time shift and you combine a time shift and time reversal, and then maybe even time scaling. And we find out that the ordering is very important. And I think here the trick is you need to remember you are doing those operations on T. Okay, so here the correct order will be you need to do the +1 first, then you do the minus, because you are keep adding something onto T. Okay, and if you want to do reversal first, then when you add, then if you do reversal first, then you need to do -1 instead of +1. And you can figure out the detail by looking back to the previous slides. Yeah. But yeah, so this kind of thing you need to be careful about the ordering. And then the next concept is the periodic signals. Okay. So periodic signals are signals that keep repeating itself from negative infinity time to positive infinity time, and they can be continuous time or discrete time. Okay. So continuous time, then you have continuous time signal keep repeating over some period big T, and for discrete time over some period big N. Okay. And so the formal definition is this. So we are using the time shift idea that we just have. So we think if we time shift the signal by some big T, so this is actually advanced, right? So if you put everything to the left by a big T, and it's still the same signal because it goes to infinity. So you can move on this one to this one, this one to this one, etc. But there is no end and tail, and so it's the same signal. And okay, so if you signal for all small t and you change xt to x of t plus big T, is the same signal, then this is periodic with period big T. And similarly for discrete time, go to small n plus big N. And so there is going to be many big T or many big N that will satisfy. Because it satisfies for big T, then it will satisfy for 2T and 3T, etc. But most of the time, there will be a smallest big T or smallest big N, and that is called the fundamental period. So the only signal that gives you trouble is if the signal is constant. Then the fundamental period for the constant signal, we just say is undefined, because it's periodic for any big T. But anyway, so assuming the signal is not a constant signal, then there is a fundamental period. And so this is the definition of fundamental period. You need to find the smallest big T satisfying this. And there is a fundamental frequency, which is calculated by having 2 pi divided by your fundamental period you just find. Okay. And so the result is the fundamental period times fundamental frequency, you will get 2 pi. Okay. So those are periodic signals. And then we have the concept of even and odd signal. And the intuition is we are saying this for polynomial of even power or polynomial of odd power. And even function has this symmetry around t equal to 0, in that if you do time reversal around t equal to 0 and flip it left and right, then it's still the same signal. And the odd signal is also have a symmetry around t equal to 0, but it's a bit more complicated. So if you swap around t equal to 0, then you will get a minus sign. Okay. So like this. And so there are very specific signals, but actually we find out that for any signal you can break them into even part and odd part by doing this. So consider some linear combination of your signal and a time reversal of your signal. Then you have your original signal plus its time reversal averaged together, then it will be an even signal, and if you take a difference, it will be another signal. Pretty easy to verify. Yeah. And then this thing you should be very familiar now. The complex number. Okay. So a complex number, it has a real part and the imaginary part, and we are using two ways to express complex number. You can either write it in the Cartesian coordinate, so the real part sigma, so the real part plus the imaginary part, or we sometimes use the polar coordinate. So we'll write using the r and the theta. And if you want to use r and the theta to write your signal, that will be e. Oh, sorry. So we didn't actually have that, but the signal will be r times e to the I theta. Okay. So this point is either sigma plus j omega or r times e to the I theta. And then we have this Euler relationship that we use a lot. So e to the j theta. Oh, sorry. So we are using j instead of I. So our imaginary thing is j. It's a square root of -1. And so we have this Euler's relation that can translate between the Cartesian coordinate or polar coordinate. And it's e to the j theta will equal to cosine theta plus j sine theta. And from this, then we can also get a reverse of this to express cosine theta and sine theta instead of the complex exponentials, because we like to express a lot of things in complex exponential. And then we have those two formulas that we use even more than Euler, I believe. So e to the j theta plus e to the minus j theta over 2 is cosine theta. And then e to the j theta minus e to the minus j theta over 2j is sine theta. Okay. And this is I call reverse Euler. I put a quote mention here because this is not a formula that people use, but we use this relation a lot, so I give it a name. Okay. But anyway, those two equations are very useful, as you should have already seen. And then the next concept is harmonic related complex exponentials. And so complex exponential is, well, it's just like this kind of thing. It's it's a signal with e to the j omega naught t with some omega naught. And but and it's very useful, as we are going to see on our review on chapter 3. But for now, complex exponential is this kind of thing, and it's periodic. But we also have this harmonically related concept. So harmonically related complex exponential are a whole bunch of complex exponential with a very special choice of omega naught. So they share some special omega naught, and the set in those harmonically related complex exponential, their frequency are integer multiple of this omega naught. So they are labeled by this integer k, k from 0 plus minus 1 plus minus 2, etc. And those complex exponential has this form e to the j k omega naught t for some omega naught. And they have this very nice property that they are all periodic, and their period, fundamental period, is going to be different, but t is all, they share one period, big T. The big T is going to be a period for all of them, and the period is 2 pi d over omega naught. And we are seeing that they are all periodic in this big T, and we can do this in reverse. And so actually most of the signal has period big T can be expressed in a linear combination of them. That's what we do in chapter 3. So those are harmonic complex exponentials. And then we see, then we want, so this is for continuous time, and we want to go to discrete time, but discrete time just complex exponential has more property that's different from continuous time. So first of all, so just for complex exponential e to the j omega n in discrete time, we find out that so this omega, even though you can pick it as any value, you can pick it as any value from minus infinity to plus infinity, but you don't need to, because it's only meaningful for omega between 0 and for some 2 pi interval, because if you change your omega to omega plus 2 pi, then because this n is always integer, so then so if you add extra of 2 pi to your omega, then you are just getting e to the j 2 pi n term, and this is just 1. So adding 2 pi to your omega doesn't change your signal at all, because you are only sampling your signal at an integer point. So we see that frequency interval is only meaningful in a length of 2 pi. So you can either pick 0 from 2 pi or minus pi to pi or something even weirder. Okay? And so the highest frequency one is, so omega naught equal to 2, for omega naught 2 pi equal to 2 pi, that's the same as omega naught equal to 0. And the highest frequency one is when your omega naught is furthest away from those 2 points. So it's around omega naught equal to pi or 3 pi, etc. So odd multiple of pi. And when that happens, your signal will be e to a j pi n. So your signal is just plus 1, minus 1, plus 1, minus 1, plus minus 1, etc. And that is the highest frequency signal you can get on the discrete time. Okay? And not even that. So for continuous time, for any omega, this will be the e to the j omega t is a periodic function. But that's not true for discrete time. Okay? So discrete time, you need to have a certain omega for your signal to be even periodic, once again, because you are only sampling points at the end. Because in discrete time, your period must be a positive integer. So your omega naught must have this form to have your signal to be even periodic. Your omega naught should be 2 pi n over n. So that means it's the rational number multiplying your 2 pi. And if your m and n don't share a common factor, so it's copulent to each other, then you can read your fundamental period here. So this n will be your fundamental period, and as we say, fundamental frequency should be 2 pi divided by n. And so if you move things around, that should be omega naught divided by n. Yeah. Okay. And as we said, if your omega naught is not a rational multiple of 2 pi, then your signal is not even periodic. So and this is very different from continuous time. And here we have our small table about complex exponentials in continuous time and discrete time. And as we said, sometimes this for discrete time, for some omega naught, this is not even periodic. And the period will be some weird value. You need to figure out this m over n factors. Okay, and finally we can go to our harmonic related discrete time complex exponential. And it's in this form, so it is still similar to continuous time. So it's e to the jk omega 9, but here we won't like to write omega 9 in 2 pi over n, because now we see that we need some special omega naught. And anyway, so we have some period bigger as the integer we pick, then we pick our omega naught as 2 pi over n. That's very nice. But then there's the other thing, so we say this k 2 pi over n should be in a 0 to 2 pi interval. So this k should only be in a 0 to so this k should be only in a bigger interval. So it's something like 0 to n minus 1 or like 1 to n, etc. So it's n consecutive numbers, because if you have k to k plus n, then you are changing you are adding your frequency by 2 pi, and that's something that doesn't change your discrete signal. Okay. So there are only n distinct k for your discrete harmonic complex exponentials. Okay. Okay. So question so far. So the complex exponentials, and just like in continuous time, although it's not in the test, it's not in a test range anymore. But we see that we have seen that for periodic discrete time signal with period big N, you can always write them as a linear combination of these harmonic complex exponentials. And that's always going to happen, because basically you are changing n variable to n variable. And anyway, so let's switch to the topic. Then we switch to those two very useful functions that we define. They are the unit impulse and the unit step. So unit impulse is like the simplest function you can think about. It's a function with 1 and equal to 0 and 0 everywhere. And you can shift this around to delta. It's called delta of n, and you can shift this to any place. You can shift this small spike to any place n naught by just changing to delta of n minus n naught. And unit step is very similar, but there are more values. So it's 0 when n less than 0 and 1 when n is greater or equal to 0. Okay. So look at this, and also you can shift this around. So you can shift this starting point to some not. And then there are continuous time. There are continuous time analog of the unit step and the unit impulse, and we also call them u and the delta. And u is okay to define, so it's 0 when t less than 0, 1 when t greater than 0. And we just say it's undefined when t equals to 0. And then we have this very singular unit impulse delta function, and we usually use it a lot. So it's a spike at t equals 0. And this spike we can even multiply it by k. And how does this infinite height make sense? So this thing is 0 everywhere, but infinite is 0. And so how does this infinite make sense is by doing integration. So we basically define this by is a shifting property on a function. So if you multiply your delta function with any function g of t, then so your delta function at t minus t0 at t0, then we'll pick out the function value at t0. And in particular, so if the g of t is 1, then you see that your delta function, when you integrate it over, it will give you a 1. And if you are integrating k delta of t, so you integrate it over the 0, then you will get k. Okay. And okay. So this delta function is very singular, but it's very useful. Okay. Any question? And if not, then let's get into systems. And okay. So I guess we skip the definition of system. System is something that has some input and gets some output. But we have many property of systems. This also you have done in homework, and I'm going to see in a test. So first property we say is memory or memoryless. So a memoryless system means that your output y of t is independent of input at any time that's not equal to t. Okay. And then there is invertible, means that so your system is x to y, and if there is an inverse system, such that for every x you get a y, then you pass your y through your inverse system and go back to some w that equal to x. Okay. So you can always get back to the same, get your input from your output. That's invertible. Then there's causality, so it's a weaker condition than memoryless. So your system is causal if your output is independent of your x over t plus tau for any tau bigger than 0. So that means that your output never depends on your input to the future time. So your output only depends on what happened right now and in the past. Okay. And then there is a stability. And for stability, we use this bounded input and bounded output condition. And that means if your input x is bounded, then your output y is also bounded. And bounded is this a bit weird definition here. So bounded means that there is a bound for your input. So there is finite number b such that for t, your absolute value of x of t will less than b. And similarly for output. Okay. So if you can find a b for your x of t, then you can find some b prime for your y of t. Okay. And then let's jump a little ahead. So in chapter 2, we see that all 4 of them we can describe that instead of this h. This h is the impulse response that we haven't reviewed yet, but hopefully you still remember them. So in terms of h of t, so h of t is something very useful to describe LTI system. Okay. So for LTI system, you can describe all those four properties in terms of h of t in some pretty simple way. So h of t, so in terms of memoryless, so all of those are if and only if. So memoryless if and only if your h of t is is a multiple of the delta function. So either for discrete time or continuous time. And invertible means that you can find another h1 of t. So this is basically the impulse response of the inverse system, and you have that h convoluted with h1 should become the identity channel impulse response, which is delta of n. And for causal, excuse me. So for causal, once again, this is a weaker restriction and memoryless. It means that your h of t should equal to 0 for t less than 0. Yeah, so it means that you put the impulse through your system, it shouldn't affect things that happen in the past. Yeah. And similarly for the discrete time case, so h of n equals 0 for n less than 0. Then there is stability. Stability in terms of h of t means that your response should not be too much. Then if your response is not too much, then your system is bounded. And we derive the mathematic saying that for continuous time system means your system should be your system response is h of t should be absolutely integrable or absolutely summable. So it means you take an absolute value and integrate from minus infinity to plus infinity, that's the infinite. And so it's a finite value, and similarly for the discrete case. And once again, this is a little confusing and bounded, so don't confuse between the bounded input, bounded output, and the absolute integral of h of t, of h of t or h of k, or h of n. So although they are both describing stability, so what's important is you don't mix the what's meaning for the bounded and the meaning of absolute value integrable. They are incomparable conditions. So some function can be bounded but not absolutely integrable, and they can also be absolutely integrable but not bounded. So they are just different conditions, and you need to be careful about what you are actually checking. Okay. Okay. No question. Then there are two more properties, and this is very important linear and time invariant property. So linear property means that, linear property means that your input 1 to output 1, input 2 to output 2. Then you take a linear combination of the input, you should get a linear combination of the output. And time invariant means that you get a time shift on your input, you will get a time shift on your output. And LTI system is a system that's both linear and time invariant. And we see that if you are a LTI system, then you can describe your system in this impulse response function h of n. So we are thinking that it's linear and time invariant. So it's linear, so how about we write our input as a linear combination of a whole bunch of delta function. Then our output will be a linear combination of the response to a delta function. But the system is also time invariant. So response to delta function to different time is just time shift of the response to the delta function. And so we arrive that we can describe the LTI system totally just by its response to delta function, this h of n. So h of n, called the unit impulse response, is the system's response to unit impulse delta of n. And y of n can be written as this convolution formula h of x of n in convoluted h of n, which is this summation. So summation k from minus infinity to plus infinity x of k h of n minus k. And you should have already seen that this is a very important formula, and then you need to remember it. Okay. Yeah. And so any LTI system can be described by its impulse response h of n. Okay. And we've seen, okay, so this thing we can go through very fast, although you are definitely going to see some question about calculating convolution in your midterm. So, but you should already have some practice in your homework. Anyway, so we have this visual way to see a convolution. So it's a summation of x of k h over minus k. Then, and so we will have some x in probably finite range like this, and h in maybe another finite range like this. And we'll think about fixing an n and see how this plays out when we plot this h of k, x of k, h over minus k in terms of k here. Okay, so x of k is just look at x of k, and h over minus k will be h of n. So first you need to do the k reflection, so you reflect around k equals 0. And then you will pull the signal left and right by having different n. So then then you want to see how those two signals multiply together and sum over k. And so if there is no overlap, then you see the summation is just 0. And so you will pull this h over minus k around by changing the n. And then there will be different kind of overlap between x and h for different n, and then you will need to analyze this case by case. So we have this n between 0 and 4, we see we have overlap between those parts. Then you do a summation, most of the time it's going to be geometric series because they are easier to summation. And then there's a different region, and from 4 to 6, then we see there's overlap here, then you do the geometric series, and etc. Okay. So this is how you analyze y of n for different n. And when you do this, then you need to be careful, don't mix up your n and k. So you are writing this in, you are drawing this in terms of k, and your output is y of n. So k should be inside the summation, and outside of your summation there should be no k, etc. Okay, so hopefully you can do the arithmetic correctly. And then similarly for continuous time, we also have convolution. So continuous time convolution. So x of t will you use x as well. Now thinking the summation of delta function is a little weird, but we have some infinitesimal analysis to make sense of it, and we have argued that we should have y of t also have this continuous time convolution form, so equal to x of tau h of t minus tau d tau. So it's very similar to the discrete time, but you have integration here. And this is h of t, once again, it's called unit impulse response. It's a response to the impulse input, unit impulse input, which is this very singular delta of t. And similarly, we have those picture way to describe the convolution, and you want to see the overlap between x of tau and h of t minus tau, and you are plotting against tau, and you are changing t to see how they overlap, and you need to analyze the different intervals. Okay. And some more notation, and this is not too important in terms of the structure of our course, but is some, and you probably want to remember that's the unit step response. So it's like unit impulse response, but instead of using a delta function, you use a unit step function u to your system. Then what you get out is this x of t or s of n So this S is called a unit step response, and it has some relation to your H, and well, you can see them here. So basically, S is the integration of H, and H is the differentiation of S. Okay. We don't use them too much, but it's nice to know. And then there are properties of convolution. Hopefully, they are already very intuitive to you. But basically, convolution is like it's like a multiplication of scalars. So it's justified with writing convolution really like a multiplication. So it's commutative, x convolute with h equal to h convoluted x, and it's distributive, and it's also associative. So it's like the elementary school properties of your multiplication, and it makes sense of this notation. And then once again, in terms of h, we have the property of our assistance, and we've already seen them, so maybe I'll skip. You can see them again. Maybe we can run through again. So memoryless means h is a constant multiple of delta. Invertibility means you can find another h such that, so this is because of association, so this is basically you are combining those two systems, and you get a delta function which is the h for the identity system. And causality means h of t equals 0 for t less than 0, and the stability, you need to be h is absolutely integrable or absolutely summable. And then, okay, so question. Okay, we are a little short on time. Okay, so let's go faster. And so we introduce this linear constant coefficient differential equation, and look at this. So the constant coefficient means those ak and bk are constant, and linear means x and y are linear. And so this is a way. So this is a equation relating y of t and x of t. So we think this as the system. So it's the x of t is the input, and you solve this differential equation, you get some y of t as output. But when you have many order of differentiation, you actually need some auxiliary conditions. So the condition that we use most is this initial rest, and it's a bit funny. It's different from like initial condition. It means that because the initial point depends on your input x of t. So we are saying y of t stays 0 until x of t is not 0. And at exactly that x of t equals 0 point, you have that y of t equals 0 for many derivatives. So this is the initial rest. And we have shown that if you combine this equation with initial rest, then system is co-integral Ti. So that's very nice, but we haven't talked about how to solve them, so it's mainly just a definition here. And we have a similar thing for discrete time case. So by instead of derivative, we just have some time delay here. So we have n minus k and x of n minus k. And the initial rest is different, so we are saying you look back n steps, all those y are 0. And once again, you for initial rest, your system is co-integral Ti. And for discrete case, the difference equation, we do have a way to solve that, and is you just change this side, so this side should have a y of n, and so you just throw everything that's not a y of n to your right hand side. So you write your y of n is something, and because it's initial rest, so you can solve. So you know your y is 0 for every point that's before your x is something, and you start solving your y of n at your initial rest point, so on x0, okay, so on n0. So you solve your y of n. You can solve your y of n equals 0 by calculating all those things. They only happen before. There are all the things before n is 0, and most of them are 0. And then you solve y of n 0 plus 1, etc. So you can recursively solve this. Okay. It's not very elegant, but you can do it. And then we talk more about the delta functions. So there are even more singular things than delta function. It's called unit doublet and unit triplet, etc. And so the unit doublet is a derivative of your delta function. Okay, so it's very singular, and but we have argued that if you want to accept it as well, it's not quite function, but you want to accept it as valid distribution that you can convolute your signal with, and then it should make sense that you take any signal x of t and you convolute it with this u1 of t, then it should give you the derivative of your x of t. And we have even more singular things, and let's just write it in a table. So we have those u1, and we have those uk. That's basically u1 convoluted k times, and that will be the k's derivative of your delta function. And you convolute your x of t with uk, and that will give you the k's derivative of x of t. And they are also negative 1, so if you have negative k, and that's actually the convolution of your unit state function k times. And you convolute x of u minus k, you will get a k's integral of your x of t. And there's something funny that you think about your unit state function in terms of this u sub k, that's actually u sub minus 1. Okay? And u of 0 is, okay, so it's not quite here, but u of 0 is the delta function. Okay. So here are the properties of the delta function and the singularity function. So I guess we can also include this table to our test. So, okay. Okay, and here are some function that are h. So if there are time delay, so if you convolute x with delta t minus t naught, you will time delay your signal. And then there's differentiation we just talked about. So those singularity function u1 give you dx dt, and uk give you dkx dtk. And there are similar things for discrete time, so difference function. But this difference function is not singular at all. It's just delta minus 1, and they give you xn minus 1 because there is no derivative in discrete time. So that's exciting. And integration we talk about, and there are accumulation in the discrete time, and that's u of n. Okay. And finally, we are going to chapter 3. We can probably do this on time. Okay. And chapter 3, so finally we go back to our complex exponential. And we find out that the complex exponentials are very useful because they are eigenfunctions to LTI system. So if you put e to the st to a continuous time LTI system, you will get h of s e to the st, and h of s is the eigenvalue that depends on s, and you can calculate it from your impulse response h like this. And similarly for discrete time, discrete time is a bit funnier because instead of e to the sn, we want to write the e to the n, but doesn't matter too much. Z is just e to the something, e to the j something, and similarly we get some eigenvalue h of z, and we can calculate h of z in this way. And anyway. So we're seeing that those complex exponentials are very useful for describing our system, because if you can write our signal in terms of complex exponential, then we can read the response to a system pretty easily. Then we found out that, well, for periodic function, we can write them in terms of complex exponential pretty nicely. So for any periodic function x of t, we can, not any, most periodic function x of t, we can write it in terms of this summation, linear combination of the harmonic complex exponentials, because you want those complex exponentials to also periodic in big T, right? And so those are the harmonic complex exponentials. And we found out that actually for most x over t, you can do this. So you can find that AK is this x over t e to the minus jk omega naught t dt integral and average over one period, so 1 over t. Okay. And so we have this back and forth transformation between periodic signal x over t and the set of coefficient, Fourier series coefficient AK. And transformation back and forth, you will get given series of AK, then you can write x over t as summation k, ak e to the jk omega naught t. And other way around, if you have periodic signal x over t, then you can find ak in the integration here we just said. Okay. And the integration is over any one period. And most of the time you just pick the period from 0 to t. And there is a convergence issue for the Fourier series. So actually not all signals, periodic signal can be written as Fourier series, but we argue that most of signals are reasonable enough to have that. And so we have given some condition that the signal is converge. And convergence, we mean the energy of the difference between your original signal and the limit of your series goes to 0. And with a continuous signal satisfies this, and if a signal has finite energy, then it's also good. And otherwise, we also have the Dirichlet conditions. And if a Dirichlet condition, then you have this pointwise convergence, although this convergence is a little funnier because of Gibbs phenomena. But anyway, it will be your signal is absolutely integrable, and finite min-max and finite discontinuity. And okay. So here we just want to say most signals are convergent. And we have 3 minutes and let's slide. So I guess let's go through this a minute carefully. And anyway, so we have this continuous time Fourier series, and so once again, a continuous time Fourier series with this back and forth transformation. So it's a condition between periodic signal x of t and whole boundary coefficient ak. So it's k from minus infinity to plus infinity. And we found out that there is some relationship between x of t and ak. So okay, so yeah. So let's say we have some x of t that has a series coefficient ak, and some y of t has a series of coefficient bk. And so everything here is periodic with period t. And we say the fundamental, and we define this omega naught as 2 pi over t. And we see that this transformation back and forth is linear. So you have a linear combination of x and y here, you get a linear combination of a and b. And if you do a time shift on your signal x, then your ak will get the extra factor of e to the jk omega naught t naught. And similarly, we have reversed. So I think we didn't actually derive this. You can derive this pretty easy. So if you shift your k, so you shift your k to k minus m, then you will get similar frequency shift. Not quite frequency shift. Similar complex exponential on your x of t. So you get the extra e to the jm omega naught t on your signal. And there's conjugation that we spend quite a bit of time talking about. So we say that if you change your x of t to x star of t, then your ak will become a star of minus k. And time reversal we didn't talk about, but hello. So time reversal we didn't talk about, but you can describe easy. You can derive easy. So you get xt to x minus t, then ak become a minus k. And then time scaling we talk about, so we say you do time scaling on your x of t, so your ak don't actually change, but your fundamental period will change. So this is like the only thing that get everything outside of your same fundamental period. It's gonna be funny. And then there is something that we're going to see more later. Quite important that if you do convolution on one side, then you will get a multiplication on the other side. And similarly, you do get a convolution on your AKBK, then you will get a multiplication on your XTYT. Although here there is some normalization difference, so you just need to be careful. So here we are actually having like a convolution of periodic function is different from the convolution. So usually the convolution we talk about in chapter 2, you integrate from minus infinity to plus infinity, but here you are integrating over 1t. And then you can think about your averaging over 1t, so you can divide the t here. And anyway, so I guess going a bit over time, but just one thing. So here is the differentiation that we derive. So you take the xdt, then you get the extra jk omega on your ak. And we have said that then there is an integration, but this is actually a funny equation. So because this minus infinity x over t is undefined, so this you probably can never use. So if you think the integration, you want to do the reverse of your differentiation. Okay. And okay, so finally there is a possible relation. Just say the energy in time domain equal to energy in the frequency domain. Okay. So sorry for overtime, and any question? Otherwise, we'll have our test on Friday. Okay.